For doing that, it is not a strict class B, because now I am now putting an additional power in the biasing circuit, but this is negligibly small, so you don't have to worry about the PDC in increasing, because the amount of increase is negligibly small. This current through this is basically to make this diodes conducting, and the amount of current may be in terms of a milliampere or something like that, so good enough. So, the current that goes through that is a milliampere multiplied by this VCC and VCC, the power is extremely small. So, this pre-biasing to take care of this crossover distortion takes care of this issue of distortion due to this crossover. Now, the output will be full sine wave output. This, to distinguish this from the previous case which I mentioned, we call it as class AB condition, because it is not A really, but I am putting some amount of biasing to make it initially start conducting. So, that is shown by saying it is a class AB condition, basically class B amplifier. Any doubts? Okay? Good. Now, let us derive what is the efficiency of this. I already said that efficiency is 78%. Where does magic number come from? Let us take the power in VCC and VC minus VCC. This power supply is a constant voltage power supply. So, the voltage is VCC all the time, and current through this is only for half cycle corresponding to when this is conducting. So, the voltage is constant and current is half sine wave. In this one, voltage is VCC and current is another half sine wave, which is the remaining other half. Okay. And what is peak value of this current? Remember that this voltage is giving rise to what is the output voltage. So, V out will be what is maximum value that this can be when this is saturated. So, all the voltage occurs here, then the maximum value will be VCC. So, VCC by RL will be equal to the amount of current, maximum current that will flow through this transistor, through the power supply accordingly. So, this peak value is equal to VCC by RL. Is the point clear? Because only conducting for half cycle, and second is we are driving it to a point where this input voltage amplitude is such that this is saturated. When this is saturated, we do not go beyond that, because then we will be cut out, there will be distortion. So, this will be 0 voltage. So, all the VCC will occur across the load. So, the peak value of the current will be VCC divided by RL, but the current duration is only half the cycle. In the second power supply, VCC's magnitude is same, but the current is now same half current. Again, the peak value will be equal to VCC by RL. In the other side. So, now how much is PDC? This is same as this, right? Amount of power supplied by this is equal to power supplied by that. So, PDC is equal to 2 times VCC is a constant into I current, current is equal to half sine wave integrated dt 1 by t right. Would you give this up notationally? How do I find the average power? Average power is Vt into It dt integrated over 1 cycle. Now, my V is constant, I is this half cycle, correspond to 0 for half and then half cycle for the other one. So, if I multiply this and integrate over dt and 1 by t 0 to t, this will give me the average power that is supplied by the VCC and also by minus VCC, because I put a 2 there. So, remember we did this exercise in the earlier class, that the average value of a half sine wave in the assignment problem you work it out is equal to 1 by pi of the peak value. Anybody remembers or not? Average value of the half sine wave is equal to 1 by pi of the peak value. So, the answer to this is 2 times VCC into peak value divided by 1 by pi, right. So, this is equal to 2 times VCC square 2 by pi VCC square by RL. What the assumption I am making? I am making assumption that the input signal amplitude is such that this transistor is driven fully into saturation. That is the logical thing to do, for the simple reason, if I do not drive it fully, I get a less output. So, idea is to get the maximum amount of AC power output. So, I must drive it such that the device will go almost into saturation. Under that assumption, this is what we get. Now, let us see what is the power output of the on the load P out. What is the voltage across this? It is a full sine wave. And what is the amplitude of the sine wave at this point? VCC and minus VCC. So, what is the average power of a sine wave with an amplitude is equal to VCC half VCC square by RL is the RMS power, right. So, this is my output, this is my input. So, what is the efficiency? And how much does it come out to be? Pi by 4. And what is pi by 4? 0.78 approximately. So, that is why I said efficiency is 78%. This is the maximum possible efficiency. If I am foolish enough to not drive it fully, then obviously efficiency will be correspondingly decreased. But I am assuming the power amplifiers operate in the best maximum amount of outputs. So, this is the maximum efficiency you can ever get. Okay. Next question is, what is the dissipation in the devices? P out, PDC minus P out, where does it go? It goes into dissipation. So, PD total dissipation is equal to 1 minus in the two transistors. Okay. How much does it come out to be? 0.22 of P out. This is in two devices. So, half of that will be in one device, each device. So, the dissipation in each device is only 10% approximately of the AC power output you can get out of the class AB amplifier. Compare this with class A, where the dissipation was 50% in the device and 50% in the output. Here I am getting 78% in the output and only 10% and 10% in these two. So, this requires a device which is rated for a lesser amount of dissipation. So, when you buy transistors for this kind of circuits, you must check what is the transistor capability. For example, if you are designing for 10 watt audio amplifier, then the output power is 10 watts. So, this must be at least rated for 1 watt minimum. So, you should increase, actually better be on the safe side, maybe take a 5 watt dissipation or 2 watt dissipation for some kind of a safety.